In this video, we're going to discuss the Gibbs energy, or often known as the free energy. For that, let's set up the situation with entropy and spontaneity. Remember that our delta S of the universe was equal to the delta S of the system plus the delta S of the surroundings. And if delta S of the universe was greater than 0, then it was spontaneous. Any process that after it completed netted a positive entropy for the universe was a process that could occur spontaneous. If instead the delta S of the universe was less than 0, if it was negative, this was non-spontaneous. This process would not occur on its own. You'd have to apply some outside source, some power system to drive that reaction to occur. And if it happened to equal 0, we were at equilibrium. Well, to know if some process would be spontaneous, we would need to know both the delta S of the system and the delta S of the surroundings. It isn't enough to just look at your chemicals entropy change. You can definitely have a negative delta S for your system as long as your surroundings is positive enough. We saw this in examples like water condensing. As your water condenses from gas to liquid, it loses significant entropy. Those molecules have to stay much closer together, they have less freedoms of motion. The delta S for condensation is extremely negative, but all that energy has to be given away to the surroundings, and net will increase the surroundings entropy more as long as you're below the boiling point. So less than 100 degrees Celsius, this becomes favorable. However, the ability to know whether something will be spontaneous or not without having to calculate the system and the surroundings would be very useful. A way that we can know whether a spontaneous reaction will occur solely from looking at our reaction would be far more handy. And this is the Gibbs energy. Remember that there's a few relations. The delta S of the surroundings was equal to the negative delta H of the reaction divided by the temp. The delta S of the universe equals the delta S of the system plus the negative delta H of reaction divided by temp. Well, if we multiply everything by negative T, we can reorganize this to negative T times the delta S of the universe equals negative T delta S of the system plus delta H of reaction. In doing this, I have enthalpy information about the reaction as well as entropy information about the reaction telling me the entropy of the universe. I don't need to directly determine the entropy of the surroundings. This term, negative T delta S of the universe, is equal to delta G, the Gibbs energy, also called the free energy. Adjusting for various signs, the delta G is going to be equal to the delta H of reaction minus T delta S. In this case, assuming we're performing a reaction, this is reaction in both cases. We can derive a new state function that allows us to determine spontaneity based purely on information about the reaction. No surrounding information is necessary. Well, since delta G is equal to the negative delta S of the universe times temp, and we want the delta S of the universe to be positive, that means delta G would need to be negative, so negative times a negative to get a positive. If delta G is less than 0, reaction is spontaneous. If your delta G is greater than 0, reaction is non-spontaneous. And in the case that delta G is equal to 0, you're at equilibrium. So we define a new term here to allow us to explore whether a reaction will be spontaneous at a given temp without knowing the actual surroundings itself directly. Given us restrictions on when it is and isn't spontaneous, we can take a look at delta G versus delta H and delta S. If delta H is positive and delta S is positive, I'll have some positive value and then subtract from it some positive value. Well, in this case, when temperature is really small, minusing S will be really small. Starting at 0, we will subtract nothing and just have a positive value. But as the temp increases, we'll subtract a larger and larger and larger number to eventually become negative. In this situation, I have an endothermic reaction, but it becomes more entropic as it occurs. So even though it takes energy to make it happen, it results in a wider distribution of energy when it occurs, which is favorable. Eventually, the temperature will get great enough to make this occur. In this case, again, think of our water example. H2O liquid going to H2O gas. This process requires energy to happen. There's a delta H of vaporization here. But it also increases the entropy, so they're both positive. While colder, water does not turn into a gas, but eventually you get hot enough that it will. This is spontaneous, but only at higher temps. Well, let's flip the signs a little bit. What if we do a negative delta H and a negative delta S? Which honestly is just the reverse of this reaction. In this case, you have an exothermic reaction, but it becomes less entropic. So gaseous water could condense. When it does so, it would give away the delta H of vaporization, but it also would become a liquid from a gas and lose some of its entropy. Well, in this case, when you subtract a negative, it's like adding it. So I have some negative value and I'm going to add some other value. So imagine some random negative 10 minus negative 1. Well, minus negative 1 would be negative 9, but as the temp increases, this will become 2. And then as the temp increases more, this will become 3 and 4 and 5. And our calculated value originally was minus 9 and then minus 8 and then minus 7. As the entropy times temp gets larger, we subtract a more and more negative number, and a negative minus a negative moves towards positive. So originally, when temperature is low, the negative delta H is adding very little and staying negative. But eventually, as temperature gets too high, it overall becomes positive. Well, once you're positive, you're no longer spontaneous, so the lower temperatures, delta G was spontaneous. Continuing down, let's do positive and negative. I have delta H, it's positive. I'm going to subtract a negative, which is going to make it more positive. If you subtract a negative, you just add a positive. So positive plus a positive, it does not matter what temperature. A reaction that requires energy to occur and ends up less entropic afterwards is always disfavored. It will always be positive. We can start with positive 10 and 0 times delta S. So we will subtract 0. We'll make this negative 1. You subtract negative 1, you add it. The total is 11. Make it 2. Subtract 2, your total is 12. Subtract 3, your total is 13. It will only ever get more positive. As a result, an endothermic reaction that loses entropy is never spontaneous at any temp. And finally, what if we're negative and positive? In this case, you have an exothermic reaction that increases your entropy. When you subtract a positive, you will get a smaller number. So if we start with a negative delta H, say negative 10, and we subtract 1, we end up with negative 11. Well, times it by a slightly larger temp, it becomes 2, you end up with negative 12. Slightly larger temp, it becomes 3, you get negative 13. Any increase in temp will only subtract a larger positive, making the value even more negative. In the event of an exothermic reaction that creates more entropy, this is always spontaneous at any temp. Thanks to the Gibbs free energy expression, we can look at just the entropy and enthalpy for the reaction to determine whether it will be spontaneous, whether it will be non-spontaneous, or whether it will be temperature-dependent spontaneity.